strong survives always. That's basically the rule of thumb in the nature. And therefore, this is a neutral solution. No acidity, no basicity. It's pH 7.0. If you have a strong acid plus weak base, you'll make a salt and water always. So for example, nitric acid, you can take a sulfuric acid, you can take a perchloric acid, you can take HCl, HBr, HI, they're all strong acids, right? Plus ammonium hydroxide, which is weak base, ammonium hydroxide. You make the salt, ammonium nitrate, ammonium sulfate, ammonium chloride, ammonium iodide, ammonium bromide, depending on which acid you took, right? Plus water. Now what will happen to this solution? Strong survive, remember. So now this is the strong guy. So our acid is strong, therefore that dominates. So the solution will be acidic solution. pH is less than 7.0. Even in principle, you can calculate exactly what is the pH of that. We are not going to go there in the mathematical calculation. No, not for this class, right? We don't need it that from that detail. But at least you should know strong survives. So if the strong acid, meaning it's acidic solution, pH is less than 7. So what's so good? Weak acid and strong base. So if you have weak acid and strong base, now here is a strong guy. Strong survives once again. An example is carbonic acid is weak acid. Acetic acid is weak acid. Phosphoric acid is weak acid. Plus, if you take strong base like a potassium hydroxide, lithium hydroxide, sodium hydroxide, all those group 1 elements, you get the salt for, in this case, potassium carbonate plus H2O, right? And now this potassium carbonate solution, what will be the nature of it? Will it be acidic, basic, or neutral? It's a strong survive. Base is the strong. It came from potassium hydroxide. Therefore, it's a basic solution. And that is pH is greater than 7.0. pH 7.0. The fourth category is, which I did not write it there, and you must write it down, what I'm writing it here, right? So if you have a weak acid plus weak base, you'll also get a salt and water, always. You get a salt plus water, H2O. Now what will happen to this solution? Basically, this is a little bit complex, but not that bad. So now in this case, what you have to compare, remember, weak acid, what is weak and how weak is weak, then we can determine by the value called Ka. Remember, right? K is the dissociation constant on weak acid. Similarly, you can also have the same thing for the base, and that is called Kb. B stands for the base, A stands for the acid. Kb is the dissociation constant of a weak base. Now you have to compare K and Kb. You'll have two scenarios. Number one, if Ka, if you're writing, everybody writing, right? This is the one I did not put it there. I want you to write it. If Ka is greater than Kb, if Ka is greater than Kb, then this will be acidic because K determines acidity, and that the salt solution will be acidic. That is, acidic means pH less than 7.0. Number two, if Kb, the base, is greater than Ka, then it will be basic. As always, here also the strong survive, but you have to have two parameters first before you compare. One is a Ka and Kb. Please write down this one, very important information. It will be one or two questions will be from the test. Okay, do not forget. So weak acid plus weak base equals salt and water. Weak acid, the strength of weak acid is determined by this dissociation constant Ka. We talked about more details, all those things last Wednesday. And Kb also determine the dissociation of weak base. Since then you can compare the Ka value and Kb values will be given to you if you are compare, right? If the Ka is greater than Kb, K strong survive acidic dissociation, it's acidic, pH less than 7. If Kb is greater than Ka, then it's a basic, pH is greater than 7.0. Do you have any questions? One or two questions will be here from these topics on the test because it's important. Yes?
I have a question. Okay, so I think you just said this, but on the test, if we have something that talks about a weak acid and a weak base, you will give us the concentration constants, right?
I'll give the dissociation constant values, yeah.
Oh.
Value of the K and KB. Oh yeah. Up to the other you cannot compare. Only thing you have to remember, remember the basic principle. If K is greater than KB acidic, P is less than 7. And if the KAB is greater than K, it's a basic P is greater than 7. Yes. Any other questions?
So I got a question. Is K is like a filling variable or do it represent something?
Now, K is the dissociation constant of an acid. Remember we talked about, right? K equilibrium times multiplied by concentration of water is Ka. We talked about, remember those equations, right? I'm going to flashing through, but don't take it, just wait there. Right here. Remember the K? Right here. Ka is right here. Ka, right here.
Okay.
Yeah. K is the dissociation constant of a weak acid. Yeah. All right. Okay. Any other questions? If not, let's move on to our next set of molecular components, set of compounds. Compound will be classified into two groups, major. There's another group there, but we are not interested in this class. One group is ionic compounds. We talked about more details, their characteristics, properties, applications. Then we talked about their salts, acids, and bases. That's another important topic of our own. It has a very important application in our health. And the next one, we'll be talking about the molecular compounds. Molecular compounds. There's millions of compounds made through those the basic the molecular compound or covalent compounds. So basically, let's go through that, right? Molecular compounds, and they are basically sharing a pair of electrons. And why do they share? What do we need to know? Why do you need to know that they make molecular compound? You need to know the number of electrons in outer shell, valence shell electrons of the nonmetals and metalloids. And we also talked about, right, metal plus non-metal molecular compounds, non-metal plus metalloids molecular compounds or covalent compounds. We talked about that, right? We'll also talk about the Lewis dot structure. You also know the Lewis dot structure of the elements so far, depending on the group, depending on the position in the periodic table. And why do they make a bond? We also talked about this is due to spin pairing. Remember, to make a one bond, you have two electrons, 1 and 1. Any kind of elements you take, let's say A and a B, any kind of bond you make with A and B, you have two electrons. Two electrons consist of a bond. Why? One electron spinning in a clockwise direction. You don't know which one. You don't have to. Another moving in a counterclockwise. Opposite spin, creating two tiny magnets, north pole, south pole, north pole. Now they attract, make a covalent bond. Very strong bond. Very strong bond. Basically, electric field is converted to magnetic field. And if you can encounter, you have done probably, whenever you put some magnet in your refrigerator, you can see it. Take the magnet slowly to the refrigerator. You can see how it sucks it through. It's very, very strong force. You can feel it even. So that's the force. Basically, it is the it is a microscopic level, the molecules, but it is a very strong force. All right, and then we'll talk about the concept of single bond, double bond, triple bond, etc., etc. We'll come back to that. All right, so this is the review, and we have done it, but I'm going to show you. If you want to write, fine. If you do not want to, you already know. The outer shell electrons of the metals, non-metals, and metalloids. That's very interesting, right? Metalloids, the carbon, silicon, germanium. They're in group 4A. If you look at the periodic table, therefore 4 electrons in the valence shell. It can make 4 covalent bonds surrounding these elements, right? Because 4 covalent of basically carbon, you have a 1, 2, 3, and 4. So you can make a 1 bond there, 1 bond there, 1 bond there, and 1 bond there. So you can make, I'm not writing which element, but you can write like this and like this, right? Let's say a hydrogen. Hydrogen has 1 electrons. You can put a hydrogen on the top. You can put hydrogen on the top and hydrogen on the top, right here. So that's a methane, CH4. The molecule is CH4, which is called methane, right? Methane. It's a molecular compound by sharing a pair of electrons. Silicon will do the same thing. You can also have a SiH4. Silicon, methane is a carbon tetrahydrate. It can say silicon tetrahydrate. All right, you can put germanium will do the same thing. These are silicon and germanium are basically the metalloids, and the hydrogen is a non-metal metal. It could be both, right? If you take the group 3 element, group 5 elements, nitrogen, phosphorus, arsenic are group 5 elements, 5 electrons in the outer shell. So maximum 5 covalent bonds surrounding these elements, they can make it, but usually they don't. But some of them will. I will show you. There's an exception there. So maximum number of bonds, single bonds, they can make 5 because there are 5 electrons in the outer shell. Usually 3 bonds are very common. Probably have seen it, right? For example, nitrogen. Nitrogen has 5 electrons in the outer shell, and as you probably remember, 1 lone pair, 1 pair, 1 electron pair, 1 electron unpaired. Right? You know that, right? 2s2, 2px1, 2py1, 2pz1. And so you can make a 1 bond there, 1 bond there, and 1 bond there. Let's say use the hydrogen. Sure, you can use the hydrogen, has 1 bond, 1 electron outer shell. Hydrogen, it can use 1 electron outer shell. And so is this one, hydrogen, right? So now you can make a bond. You can make it like this way. All right. And what is this one? Ammonia, NH3. We talked about just few earlier, right? So ammonia. Same thing, you can make a PH3. Phosgene. This is called phosgene, PH3. You can also make the same thing. You can make the arsenate trihydride, ASH3. Same way, exactly the same way. You have a lone pair there, and so they make a maximum, but they can, if you allow them with a Hertz condition, these lone pairs will be used to make a bond. Remember, when you make the covalent bond, metals are surrounded by those lone pairs in oxygen specifically, make a hydrogen shell. So they can be used, but depending on Hertz conditions that you use. But usually 3 bonds are very common, as I said. So oxygen, sulfur, selenium, they're group 6A. That means they have 6 electrons in the outer shell. So maximum 6 covalent bonds you can expect. But usually they make only 2 bonds. Why? Because remember, oxygen, right? Oxygen have 2 pairs of lone pair or unbonded pair of electrons, and you have a 1 unpaired. That is our 2py1, 2pz1. If you remember that structure, right? And this is 2s2, for example, and this is 2px2. So 2py1, 2pz1, and now you can do the same thing. Another electron from somewhere, and usually hydrogen, for example. If you have hydrogen, now it will make a hydrogen, it's a covalent bond. Same thing here. So 1 bond, 2 electrons, twin pair, and that's H2O. Now, does it mean that oxygen cannot make? Oxygen is the exception for some reason. It never uses, it uses these lone pairs only to coordinate cations and anions, usually the cations, because it's a negative charge, right? But otherwise, usually not used very frequently to make a 6 covalent bonds. It doesn't do that. Sulfur does, and I'll show you some. Sulfur, selenium does. So sulfur, for example, very similar. You can also have the same thing. So group 6 element, right? Exactly the same way. You can make like this. You can make like that. And let's say use hydrogen. That's fine. You can use hydrogen, so you can make bond. You can also make a hydrogen bond like this. Is hydrogen sulfide, stinky gas, rotten egg, H2S, hydrogen sulfide or dihydrogen sulfide, either way, right? So we are also giving some names, how to name the covalent molecules too, right? Hydrogen the typical name is a hydrogen sulfide or dihydrogen sulfide. Dihydrogen oxide, we don't say that, but we say water, H2O, very common stuff. Ammonia, NH3, you can say hydrogen nitride, nitrogen trihydride, you can say that, but usually ammonia, NH3. Phosgene, PH3, you can also say phosphorus trihydride. Yes, you can say that if you want to. But same way, the naming is 2. You can do the selenium very similar way, exactly the same way. Now, if you go to group 7, those are halogens, right? Fluorine, chlorine, bromine, iodine are group 7 elements, and it has 7 electrons in the valence shell. So maximum 7 covalent bonds you can expect, but usually it doesn't happen. Why? Because 3 of them are lone pairs. If you have an unbonded pair of electrons, they're already very stable. But if you use a very harsh condition, then you can. And remember, one is that Cl2O7. Remember Cl2O7? Cl2O7 reacts with the water, makes the perchloric acid. In this case, all 7 electrons are used up. All of them are used up to make a covalent bonds, right? But usually they make 1. So let's say if we take a, so let's say if we take a X is a fluorine, chlorine, bromine, right? X is the fluorine, chlorine, bromine, iodine. So it is one pair, another pair, another pair, another pair. Those are all unbonded pair of electrons. One is unpaired, and it's a octet rule, remember? So you can do the another electron from anywhere, and it can do the Y, all right? And it can make a compound like this. So Y could be any type. It could be hydrogen. It could be X. It could be X2, right? It could be X means it could be fluorine, chlorine, bromine, right? Cl, bromine. Remember the diatomic elements, right? Bromine, iodine, etc. It could be like that too. And it could be hydrogen. If it is hydrogen, you know, HCl, HBr, HI, etc., right? We already talked about it. So that's basically the number of elements, number of electrons in outer shell, and how many of them are they can use maximum, and how many of them are routinely used are this given to you. Group 80 elements, noble gas elements, inert gas elements, they have 8 electrons. And all those things, elements, they're doing it, they're sharing pair of electrons just to have 8 electrons in the outer shell. That's because they're doing it. For example, let's say water. Remember, water has 2 electrons right here, 2 electrons right there, right? They're sharing. Since the oxygen is sharing, oxygen can share 2 electrons here, 2 electrons there, and 4 electrons there. 8 electrons, 2, 4, 6, and 8. Octet rule. Sulfur, 2, 4, 6, and 8. Octet rule. So they're following the octet rule. Hydrogen is the exception. It doesn't follow the octet rule because it doesn't have, it cannot accommodate more than 2 electrons. That's basically sharing 2. Why? After sharing 2 electrons, the configuration of hydrogen is becoming helium, He. Helium is stable, so it is stabilized. Oxygen is stabilized because it's taking 8 electrons to sharing and adapting a configuration very similar to neon. Neon is inert gas. This one is argon, and so on and so forth, right? So that's basically that's follow the octet rule. Same rule applies. So now if we go back, go down, go next to that. So this is the procedures how to write the molecular compounds and naming it. I'll go to the general principle, right? So before I do that, let me see. Before I do that, so so let's go to the general principle first. And once again, this is a general principle. That's I put I, X, Y, Z, huh? And then we'll give you plenty of examples. So don't worry. All right. So let's say non-metal plus non-metal is the molecular or covalent compounds. Molecular compounds or covalent compounds. Example, let's say if X plus X, for example, it will make X2. And you know that. Hydrogen makes that one. Hydrogen is H2, nitrogen is N2, oxygen is O2, and your fluorine is F2. So chlorine, bromine, they're all basically diatomic elements, right? We talked about earlier. So they're all diatomic elements. And they're basically making covalent compounds, diatomic elements, but it's a covalent molecule anyway, right? Likewise, you can have 3 of them together, or you can have more. 3 plus more, 2 plus 2 and more, or 3 and more. Then if you have Xn, for example, if n equal 4, usually phosphorus. Phosphorus usually exists as a P4, by the way. Phosphorus exists as a P4 in nature. If you take a phosphorus atom, you can take the phosphorus, basically it burns very nicely, it gives a light, it exists as a P4. Likewise, sulfur exists as a S8, 8 of them are together. And so basically what you have to do, it's a circular, you put a S, and all of them, and then all of them are linked together. Same thing, the P. So basically they're sharing electrons to make a bond and making the P4 or S8. Usually there, not too many of these are known, but P exists as a P4, just like a diatomic element, hydrogen, oxygen, fluorine, chlorine, bromine, iodine, they use as 2 diatomic elements. Phosphorus is a tetra, 4, and it is octa, 8 of them, sulfur. So those are the basically same molecule, same atoms, right? Same atom together. The simple ones. Let's go to a little bit complex one. So if you have a X and OI, these are the coefficient numbers, right? And then make a Xn and Ym, or n equal 1, 2, 3, 4, 1, 2, 3, m equal 1, 2, 3, etc. So that's basically molecular compound. And this one we'll talk about more details. We'll come back to that, right? So this is general principle. And depending on the molecular, we can talk about, for example, let's say I'm going to do this one, let's say N2 or N2 plus oxygen, nitrogen with oxygen. You can make a series of compound. For example, you can make NO when n equal 1, m equal 1, right? You can also make a compound looks like this, N2O. All right, it's a dinitrogen oxide. It's a laughing gas, by the way. And you can also make a compound with the nitrogen and oxygen and looks like this, NO2, sorry, NO2, nitrogen dioxide. So nitrogen monoxide or NO, dinitrogen oxide. That's a by the name, how to name it. Okay, I'm also giving the name. So if you please remember, please write it down. Nitrogen and oxygen, they can combine covalent bond. I will show you the covalent bond. All those will show it in the structural form. So nitrogen NO, nitrogen oxide, right? Nitrogen oxide, nitrogen monoxide, you can say one mono oxide. Dinitrogen oxide, the laughing gas. If you have a little bit in your room, or little bit in it's a large room, for example, if you have a little bit of this gas, oh yeah, everybody will be laughing for hours. It's a laughing gas. It's a laughing gas. Nitrogen dioxide, just like a sulfur dioxide, carbon dioxide. Those are all basically nitrogen dioxide. Nitrogen di means two, oxide O. Nitrogen dioxide. All right. Nitrogen, yes.
So N2 plus O2 can equal any, or can like combine to be any of those three products.
No, not three. I'm going to give you more. Just
But like,
yeah.
but it's not like just one like product. Like there can be multiple products.
Depending on the condition. Yes, the conditions.
Okay.
Yes, condition will allow to make different type of compounds. Yes, that's so. Let me give you another one. It's not. Nitrogen makes so many compounds. Yes.
This is kind of a dumb question, but I don't get how you put those two together, because like NO2, then where does the other N go?
I'll show you. I'm not balancing it. You're not dumb question. I didn't balance it. I will show you the balancing and everything. Will come back to that. So we are just going through. We are going through this principle, N and M principle. Yeah. So hang in there, okay? All right. So I didn't balance it, by the way. I'll give you some of those. So nitrogen and oxygen can also make a compound looks like this, N2O3. You have seen it before, because N2O3, when it makes the water dissolve with the water, it makes the nitrous acid. The last but not the least, nitrogen and oxygen can also make a compound is dinitrogen pentoxide. Dinitrogen trioxide, this dinitrogen pentoxide, penta 5 pentoxide. I'm just showing this schematically. I will give you the details of the when I go through each and every compound, and we'll talk about the structure, how the bonds look like, what are those things, everything. Just hang in there, okay? All right. This is the general principle how to make the compound. I give you one such example for what this lowercase n, lowercase m stands for. X and Y, the two things, for example, and you can make many of these. So was so good?
I have one more question.
Yeah.
Okay, so it says NX plus MY. Is the N the coefficient or the number, or is it the element?
N is the coefficient.
That
N
was
is
a
the
dumb
coefficient.
question.
M is the coefficient too. Yeah, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, etc., etc., etc. Right. For example,
Okay.
Let's say N2O5. So N lowercase n is 2, and M is 5. Yeah, the coefficients. All right. So that's the one set of molecular compounds, right? With a non-metal plus non-metal. How about non-metal plus metalloids? You can also have molecular compounds too. Non-metals plus metalloids, also same thing. Pa plus Qb. P is the coefficient, Q is the coefficient, the number, and you can make a AP and BQ. Where A is the non-metals and B is the metalloids. Once again, P is the same thing, 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. Same way you can do that, right? For example, let's say one such example, if you want to, let's say silicon, right? Silicon plus H2. And with just one example is good enough for the time being. We already have some, and that is called SiH4. SiH4, silicon tetrahydride. Okay, tetra is 4, right? I didn't balance it, by the way. We can balance it. You can put a 2 there, but those are, so now you can have like this way. Okay, all right. So that's basically, and also CH4. Remember, carbon plus hydrogen. Also, all the carbon is not in the non-metal, in the metalloid group, but it's a non-metal. And you can also have a CH4. Once again, it's not balanced. All right. So that's basically the non-metals plus metalloids. They can also make a molecular compounds. Now, I'll give you some example of this. Not too many, but I'll give you quite a plenty down the road. Just hang in there, okay? I'm just giving this general principle. The last but not the least, a carbon compounds. Carbon plus non-metals. Carbon plus non-metals. It makes a series of molecular compounds. You can make millions of molecular compounds. And that class of compounds, as you probably know, I'm not going to go through the details of those. I describe the compounds in a different way. Organic compounds, don't be scared of it. Many people are, but don't be scared of it. These are just like the molecular compounds. So carbon plus non-metals make it millions of molecules. Nature makes millions of molecules. Research laboratories synthesize many molecules, and many of those molecules are pretty large. One such molecule I gave you the indicators yesterday, or the day before yesterday, indicators, and they can make those large molecules they can synthesize. They're all molecular compounds. They have different properties. Many of them are medicines and the drugs, RX drugs. And they're the many inhibitors of the enzymes, proteins, etc., etc. All right, so that's basically carbon compounds. Carbon plus non-metals make a series of thousands of molecular compounds. Question you can ask, why carbon? Carbon is usually not a non-metal. It is not a non-metal, but you can say strictly speaking, it's not a non-metal, but yeah, maybe. And it is not a metalloid either. So why carbon? Here is the principle. Carbon has 4 electrons in the outer shell. Everybody okay, right? So carbon is the 6th atomic number. And what you have a 1s2, 2s2, and 2p2. Everybody knows that, right? We have talked about in details. So it is a 4 electrons in the outer shell. That's why we talked about 4 electrons outer shell means it can make a 4 bonds, maximum 4 bonds. It can make a 2 bonds, it can make a double bond, triple bond, etc., etc. These 4 electrons are used. And as you probably saw in excited state, it will become a 2s1, 1s is still 2s1, 2px1, 2px1, 2pz1, 2py1, and 2pz1. All right, in excited state. So basically, these 2 electrons from S cell to S goes 1, 1, 1, 1, 1, and these can pair up with other metals, non-metals, not metals, non-metals or metalloids, and then make a compound. Question is, why carbon? Now, is it possible? Can carbon make a ionic compound? To make ionic compound, you have to remove all 4 electrons, right? That's because carbon will become C4+, right? Just like metals lose electrons. Let's assume the carbon can lose 4 electrons. It is impossible to get rid of 4 electrons. Impossible. To get rid of 1 electrons, you have to provide some energy because they are held by the positive charge in the nucleus, right? So to get rid of 1, for example, from here, you need some energy. Then become carbon plus. Then if you want to remove another electron, it will be carbon 2+. If you remove another electron, carbon 3+. The 4th one to remove carbon 4+. Carbon 4+ means you have to provide lots of energy. This is called potential energy. And or ionization energy supplied to remove the electron from the outer shell. And if you have to use tremendous amount of energy, which is impossible, virtually impossible. Therefore, carbon cannot lose 4 electrons to become C4+. In other words, it cannot make ionic compounds. How about can it take it? So for example, remember non-metals, they take electrons. How about carbon? Carbon has 4 electrons. Can we give 4 electrons? We can give it to px2. So we can give another 4 electrons to make 6. It's possible. So to give you 1 electrons, energy will liberate. Once it becomes negative charge, carbon C minus, another electron coming, C2 minus, another electron coming, C3 minus, another electron coming, C4 minus. It's impossible. Lots of energy needed to become those C4 minus. So carbon has no choice. It cannot release 4 electrons, lose 4 electrons. It cannot accept 4 electrons because 4 electrons releasing become helium, accepting 4 electrons become neon, right? But it's impossible. Therefore, it has no choice but to share a pair of electrons. And that's basically the beginning of those carbon molecular compounds. Molecular compounds to the carbon. Molecular compounds to the carbon. All right. Now we'll go to the example. Does anyone have a question so far? Because this question could be asked easily. Why carbon cannot lose 4 electrons? Or why carbon cannot accept 4 electrons? What's the problem here? The problem here is too much energy needed either way. Therefore, it's impossible. So that's why group 1A, 2A, 3A, we stopped it right there. All those metals, they can lose electrons. 5A, 6, and 7A, they can accept electrons. It is 3, 2, and 1, fine. Once you go to group 4A, that's a carbon family, impossible to get it. Impossible to get 4 plus or 4 minus. Anyone has a question? Why the carbon makes the molecular compounds and what is the rationale for this? All right.
So the reason why carbon can't share or lose accept or lose electrons is because it is too much energy needed.
Yep. That is the only thing. Too much energy needed to get rid of 4 electrons. Too much energy required to put 4 electrons. Either way is important. Yeah. All right. Shall I move on? Okay. Now we'll have plenty of examples. Okay. These examples are basically we talked about. Sorry. I already gave you some, but I'll give you few more probably like this carbon and hydrogen. So nitrogen, I already gave the example. The carbon dioxide, let's give carbon dioxide right here because I already gave you the example of this, right? I already gave you the example of this one. You don't need it to the whiteboard at this moment. H2O, H2S, I already gave you. H2S and H2O, you already saw that previously. HX, fluorine, chlorine, bromine, iodine, and that's another one. So let's say fluorine, bromine, iodine, for example. Hydrogen has 1 electron, right? Hydrogen has 1 electron in the outer shell. And X, which is fluorine, chlorine, bromine, iodine, it has a 6 electrons and 1 electrons right there. And therefore, you can make a covalent bond. So that's our HX. F could be fluorine, chlorine, bromine, and iodine. I already gave the example for nitrogen, NH3. I also give the pH3, etc., right? So let me give the carbon dioxide. Let's see how can we make the carbon dioxide. So remember, carbon has 4 electrons, right? 1, 2, 3, and 4. All right. And oxygen has 2, 2, 2, 2, and 1 and 1. Right? You can also have another oxygen this side probably. So 2, 2. 1, 2, and 1. All right, and let's say, well, if I show it like this way, and that's fine. And let's put this one is unpaired right here. So these are the paired. This is the paired, and this is the unpaired. So 2 unpaired and 2 paired. So now carbon has 4. So how they will accommodate to make a compound? So basically, these 2 lone pairs, these pairs of they're not available. Only these unpairs are available. So what will happen is as follows. So it will make like this. So let's put it like this way. So we have a carbon, oxygen, oxygen, lone pair, lone pair, lone pair, lone pair, and lone pair, lone pair, and lone pair, and lone pair. 2 unbonded, 2 unpaired, 1, 1. And carbon has 4, right? So let's put them together like this way, like this. And this also has a 2, these are the unpaired ones. Now what will happen? The carbon has a 4, carbon has 4, right? 1, 2, 3, 4, 1, 2, and 3, 4. So carbon has 4 and oxygen has 2. Now they will pair up. They will also pair up like that. So basically, you have a carbon will make a double bond with oxygen. Carbon will make a double bond with another oxygen. 2 plus 2, right? 2 plus 2, 4 electrons this side. 2 plus 2, 4 electrons this side. So carbon has 8 electrons. Carbon can share 8 electrons. Octet rule, right? Remember the octet rule. They share pair of electrons to make a bond to fulfill the octet rule surrounding those elements. Exception is the hydrogen because it's helium configuration. So how about oxygen? Oxygen is also sharing 8 electrons. How? 2, 4, and 4, 8. 2, 4, and 4, 8. So this is happy, make 8 electrons out of sharing 8 electrons, octet rule. This oxygen is happy, octet rule. Carbon is also happy with octet rule. Carbon dioxide, right? Similarly, you can do the same thing with the sulfur. There's a sulfur dioxide, for example. I'll come back to the sulfur dioxide very soon. So let's say, let's go methane. I already showed you, right? So methane, for example. So let's say carbon compound methane. So let's say go C. Carbon, we're going to do this one, right? CH4, CH4. Let's see how to build up the CH4. So basically, what happened? Carbon plus hydrogen. Carbon and hydrogen can make series of compound. I'm not balancing again. It can make like this. One such compound is CH4. Well, let's see how it is made. We'll show you within a minute, within a second. It can also make a compound like this, C2H6. It can make a compound like a C2H4. Let's put a C2H4. It can also make a compound C2H2. It can make many other compounds too. I'm giving this general some of those. It can make a, so one carbon, 4 hydrogen. Carbon, 4 electrons, outer shell, 4 electrons, and 4 hydrogen comes in the form of 2 molecules of H2, right? You have 1 hydrogen here, 1 hydrogen there. You can make a bond. You can make a bond. You can make another hydrogen right there. You can make a bond, right? You can also make another electron. Let's look at electron here. Make a bond. So CH4. Hydrogen is sharing 2 electrons. Helium configuration is a happy 1s2. This hydrogen is also sharing 2 electrons. 1s2, 1s2, 1s2. So hydrogens, all 4 hydrogens are happy, right? Carbon 2, 4, 6, and 8. 8 electrons surrounding. So that means octet rule. Octet rule. How about this carbon? How about this molecule? So this molecule, what you have a carbon, another carbon, and you have 4 hydrogen. You have 4 hydrogen. This 4 hydrogen. So carbon has 1, 2, 3, and 4. 1, 2, 3, and 4. Right? You have a 4 hydrogen. Sorry, let's go back. So 4 hydrogen. So let's put a 1 hydrogen here. Let's say 1 hydrogen here. 1. You can put like this. 1 hydrogen here. This you have to share equals here, right? You can just it's one single one, huh? Likewise, you can do the same thing here. 1 hydrogen there. Spin pairing. Make a bond, and another hydrogen here. Make a spin pairing. Fine. Now, and also there is a carbon-carbon bond. They can also make a spin pairing. So now what happened? Can someone tell me what will happen to these unpaired electrons, 1 and 2? There are 2 of them there. What will happen to them?
If they bond, doesn't that mean carbon has a double bond with itself?
That's our concept of double bond. That is absolutely right. That is absolutely right. So this one will come right here. Right here. This one will come right here. That is correct. Absolutely. And right here. And now you can make a double bond. So carbon-carbon double bond. So basically what you have H. I'm writing with different way. H and H, 2 bonds. C, put it C. H and H. That is right. That is right. That is absolutely right. So this molecule is called methane. Everybody knows, right? Probably I think I gave the name before. The same, huh? THANE. Methane. That's our methane CH4. This is the ethane. This is the our ethane. It's not ethane. It's ethylene. Ethylene. Huh? Say it again. Say it again. Yes. Yes. Is the time is up? No. What's the time? I think I have some time. I have 2 minutes, right? Okay. All right. So let me give you one more. So carbon, hydrogen says ethylene. Ethylene. The last one. This one. let's use this one. Very similar principle. Someone already told me that double bond, how to make a double bond. Excellent. Now let's go to the C2H2. That's the one. So you have a C, one electron, and we have a two hydrogen. So let's give a equal distribution and make like this. All right. Another hydrogen this side and this side. So now what will happen to this? Now carbon-carbon bond, they also make it two. Now what will happen to this? Exactly the same principle. Someone told me, will they make a double bond? Yes, they will make. Now what will happen here? Who can tell me what will happen here?
It'll make a triple bond.
Yeah, very good. Same principle. So let's say like this, one double bond. This one will move to this, like this, and this one also will move to this. Let me make a triple bond. That's acetylene, C2H2, methane, ethane, acetylene, ethylene, methane, ethylene, acetylene. These are concept of double bond and triple bond. Now, one of these bonds, C2H2, one of these bond is called pi bond. One is called sigma bond. All of them are sigma bonds. Sigma bond, sigma bond, sigma bond, sigma bond. One is pi bond. And this case, sigma bond, and two of them are pi bond. Pi bond, and inside one is a sigma bond. So on carbon-carbon bond, they make it is a sigma bond, and these two additional electrons from both carbon, they are making two bonds. They're called two pi bonds. So acetylene C2H2 has two pi bonds, and ethylene C2H2 has one pi bond. So that's the concept of double bond and triple bond. And we will continue. I think I have. It's okay. Do you have any questions before I make it? So concept of double bond and single bonds are important, and it will be in the test one way or another. It will be the test how to what are the in the double bonds, how many pi bonds are there? In the triple bonds, how many pi bonds are there? And what are those pi bonds anyway? Those pi bonds are additional electrons. When the sharing, they have to share together to make a bond, covalent bond with a carbon-carbon specifically here. And these pi electrons are in fact mobile. What is mobile means? They can fluctuate. They can make it break, they can make it break, make and break, because remember they are making carbon-carbon bonds, right? They call mobile pi electrons. All right, I'll continue with other things like sulfur dioxide, trioxide, these thing, and carbonic acid, the little bit larger molecules, a complex molecule. I'll continue Monday. Do you have any questions? Does anyone have any questions? Yes? All right. If not, then we are done for the weekend.